I'm Jim Jeans. I'm the analysis lead of the composite crew module. The analysis group is responsible for determining the thickness and the strength of the vehicle. We work with the design groups and the materials groups to, as a team, determine what the vehicle looks like. The vehicle, obviously, it's a crew module. It sits on top of the rocket, launched into orbit, so there are launch load cases that we have to consider, and a load case is an event that applies forces to the structure, be it pressure and acceleration due to launch, just the weight of the vehicle, the weight of the people inside it. So we have numerous load cases. We have on-orbit load cases, so when it's on orbit, it's being pushed and pulled, it's being pressurized. The vehicle can carry up to 6 astronauts to the space station. It can carry 4 astronauts to the moon and back. Then there's docking, there's on the way to the moon, the Earth departure stage is pushing us with the lunar lander attached. So there's all these different things that come together that generate a set of load cases that have to be analyzed for. All those, we go through a design cycle, we propose a vehicle shape, we size it, we calculate margins. Anywhere we have extra material, we take it away. Anywhere we need to add material, we add material, and we do it again. And it's a cyclical process. While we're doing this, or we do this using computer software, we have several programs. There's Nastran, which is an analysis package that basically solves for internal forces. To give some idea of the forces we're dealing with, this is a scale model of the crew module. It's roughly 12 feet in diameter. It's about 10 feet high. Maximum design pressure is 31 psi. The air pressure around us is about 14.7 psi, so if that's 1 atmosphere, we're designed basically to 2 atmospheres. The inside pressure can be twice the pressure we're at right now. Have to be twice the design pressure of what the space station is at. So that's one of the load cases. We also have a launch load case where the vehicle is accelerated vertically at about 3 to 4 Gs. We have an abort load case. Something's going on with the rocket underneath us. We want to save the astronauts. There's a structure mounted above this vehicle with rockets on it. If they sense something's wrong, they fire those rockets, they release us from the spacecraft, and this structure gets accelerated away at about 17 times the normal force of gravity. To give some idea of the amount of load that we're talking about, the average car weighs about 2,500 pounds. Each of these fittings can withstand about 70,000 pounds. So it's like 35 cars hanging off of one of these fittings. And all 6 of those are loaded at the same time. So total forces were in the 400,000 to 500,000 pounds, or say A747 fully loaded is the total force that this vehicle has to withstand. So the role of the analyst, right? So the design is conceived of by a team. It's not just the designer, it's the designer and the materials and the analyst, and sometimes even as far down as how are we going to test it. That team conceives of a design. And as the design evolves, the analyst has the role that it's their job to guide the design such that the analysis will close, right? We need to be able to come up with an answer that shows that the final design will work, right? So if the designer is going down a path where that's looking like it's not going to work, and I don't have enough analysis behind that design to say I can get there, we have to guide the design to come back into something that we can get our arms around it, come up with an answer that, yep, that'll work. It may not always be the most optimum design, but it has to be a design that meets our form, fit, and function, meets our requirements. We have a lot of requirements. So we got to be able to get all of those things in a box and say, we're good. When that's done, we build our article, bring it to a facility like we're in here, and we test it. What we have right now is our article mounted upside down. We're in a test fixture, and we're pressurizing it, we're pulling on it, pushing on it. And we have strain gauges, or the ability to measure the local deformations so that we can determine how much load is there. And we run it through a series of conditions. We've done about 9 conditions on the article right now. Our big one is pressure. We pressurize it. We want to know how it's stretching and deforming. We measure that, we monitor it real time, and all that data comes back to us and confirms that our simulation of the design was accurate or it was inaccurate. Did we do a good job, or did we miss a few things, and do we have to make some changes and go back and update our analysis to match what we actually got in test? A good analyst is a guy who can who can look at a problem and have enough understanding of the physics of the situation to say, yep, I can make that work, or no, I can't make that work. And then you have to go into the details of what you're working. You have computer simulations that we can run, and we have hand analysis that we can do. We have to do all that. The good ones can see it, right off the bat. You can just see it and make it work. It's hard. I do it because I like numbers. I've liked numbers, and there's a right and a wrong answer, right? So for a guy like me, getting a right or a wrong answer, that's easy. I liked it in school. If 2 + 2 = 4, it equals 4 every single time. That's what I'm good at.